right, so hi everyone. Let's get started. So welcome back from lunch. So as you know, this tutorial is about active learning from theory to practice. And I'm delighted to introduce our two speakers today. Our first tutorial speaker is Rob Nowak. Rob is a nose-push professor in engineering at the University of Wisconsin-Madison. He's one of the leaders of the field with a variety of interesting results at the intersection of signal processing, machine learning, optimization, and statistics, including seminal results in active learning, which is the topic of the tutorial today. Okay, and our second speaker is Steve Haneke. He is currently a research assistant professor at the Toyota Technological Institute in Chicago, and he works broadly in learning theory. And just like Rob, he has done a lot of seminal work on active learning. And so we're really, really excited to have both of them here today telling us about active learning. So, thank you.
Thank you, Nina, for that great introduction. It's a real pleasure to be here, and I'm really thrilled to see so many people out in the audience. I hope you can learn a lot during this tutorial, and we'll be around to answer questions and so forth. And I'll explain a little bit about the format in a minute here. I just wanted to mention that Steve and I have probably, and Nina for that matter, we've known each other since those two were graduate students. I was already a professor. I have to admit I'm a bit older. But I've known them for many years. We've worked together on organizing things and all sorts of stuff, so it's really nice to be together with them today. So this tutorial is going to be about active machine learning, and we're going to be largely focusing on the theory aspects of active learning, but I'm going to sprinkle in some of the practical applications and so forth as we go. And I'd also be happy to talk about some of that practical stuff in the breaks and during questions. So here's the outline for our tutorial. We're breaking it into 4 parts. The first part's going to be an introduction, and I'll do that. That'll be about the first half hour. Then Steve will take over for parts 2 and 3, which will be really diving into the theory of active learning and then discussing some advanced topics and open problems. And then I'm going to wrap up talking a little bit about non-parametric learning. This is going to be really kind of talking about some very, very ongoing work that I'm doing with some other folks too, so I hope you'll like that. And I'm noting at the bottom here that the slides for all of our parts here are available on that URL there. So I'll flash that up again at the end of my first part here, but if you want to follow along, the slides are online there. So what we're going to do is we'll do these 4 parts. During, maybe just given the size of the audience and so forth, it might make sense to take questions after each part. So after part 1, we'll take a little time for some questions. People can come up to the microphones again after parts 2, 3, and 4, and we'll do it like that. But if there's something really confusing or bothering you while I'm speaking, jump up to a mic and just say, hey, Rob, I don't get what you just said, and I'll try to field it right there on the spot. Does that sound like a good plan? Awesome. Okay, so I have to kind of be a little bit in control here. Normally when I give talks, I'm running around on the stage, moving around, pointing and things like that. But for this one, I have to stay here at least within facing this microphone. So I'm gonna, if I walk away and you're saying, Rob, we can't hear you anymore, yell out and tell me. So here's the conventional machine learning pipeline. The way it works is we have a large unlabeled data set. I'm showing it here in the case of an image classification problem. And what we do is we take a subsample of that very large unlabeled data set, and we ask a human to annotate some subset of it. So we get some human labels for things like dogs and boats and so forth. That gives us a smaller set of labeled data. We turn that over to a machine learning algorithm. It tries to then learn a predictive model mimicking the labeling process that this human expert is doing. So that's a conventional pipeline. And it's been really successful. These are just a few headlines. They're a few years old now, but they kind of capture all the excitement that has been going on in the machine learning area recently. And All Systems Go is actually the title of a Nature journal article talking about the success with the game playing system that AlphaGo. So all systems go, that's true, except when you kind of start to look under the hood. training these machine learning systems takes a huge amount of human effort in many cases. So millions of labeled images required, say, for ImageNet. For translation, these machines are learning to translate between languages by effectively reading more text than a human could ever learn in a lifetime. And in game playing, they're learning by playing more games than even my teenage son can stomach. So this is kind of a little bit of a confusing sort of situation. Machines are doing fantastic things, but they're not exactly learning the way humans are learning. And so there's a lot of interest and active research right now in trying to figure out how we can train machines with less labeled data and less human supervision. So the approach that we're going to talk about today specifically is active machine learning. And this picture sort of modifies that earlier pipeline to show you how active machine learning works. The idea is that rather than just taking a random subset of the unlabeled data and asking our human expert to label it, instead we're going to design an extra algorithmic component to the system, which is a data selection algorithm. And that data selection algorithm is going to be looking at all the unlabeled data as the machine is learning and judiciously selecting specific examples and asking the human expert to label those. The idea is basically the machine, as it's starting to build up a model of how to predict, it will flag confusing or cases or examples that it's very uncertain about and ask the human expert for help on those specific cases. So let me just kind of explain this idea with a motivating application here. This is something that I've worked on a bit with people in health and medicine. They're interested in developing machine learning systems that can predict disease outcomes from electronic health records. And this kind of closed loop, human in the loop, active learning process looks something like this. We have a large database of unlabeled electronic health records. We have a team or an individual human expert who provides labels to a machine learner. Labeling one electronic health record can take an expert several minutes to do, so it's a kind of expensive labeling process. And these experts are clinicians who typically get paid maybe $100, $200 an hour. So these labels are expensive. And the idea is that we're going to try to get that human expert or team of experts to label some subset of these electronic health records to teach the machine. And the active learning idea is that as the machine is learning to build up this model, it's going to automatically select specific unlabeled electronic health records that it wants the team of experts to label. So just kind of at a very high level, one of the most intuitive ways you might go about this active learning process is depicted in this figure here. So I'm just showing you two features from an electronic health record. Typically, we're looking more at like 10,000 different features or so, but to visualize it, we'll just look at two. So suppose we have electronic health record feature 1 and 2. Those are our horizontal and vertical axis. The gray dots are unlabeled electronic health records, and the red and blue dots are labeled ones. So we're labeling into two classes, say disease and no disease. And that dashed green line is the best linear classifier. So if we're thinking about which example to label next, the conventional machine learning pipeline would just pick one of the unlabeled examples at random and ask the human expert to label it. And that would give us a certain learning curve. So as we collect more labeled examples, of course, the error rate of our classifier will improve, go down. An active procedure would somehow, the machine would decide, well, which examples is it more uncertain about? And for example, a natural heuristic is to look at examples that are unlabeled and close to the current best decision boundary, like the orange one I've circled here. And the idea is that hopefully that by strategically selecting those examples that are most confusing, this will help the machine quickly learn a good predictive rule and reduce the total amount of human supervision required in this learning task. So this is just some experimental data from some actual electronic health record cases. We have about 11,000 patients here, roughly 6,000 different features that we're looking at, and we're basically using an active version of logistic regression and also a passive version. And you can see that in this particular example, active learning was able to reduce the number of labeled examples needed to learn a good classifier by roughly 50%, about half as many required. So there are some significant gains that you can get, especially in cases where the human labeling is very, very expensive. So one of the things why you say, well, that's great, why don't we just always do active learning? Well, one of the reasons is that it's a little hard to implement these things. You're having sort of an online learning system as soon as you activize it. That becomes a much more intensive process. It's not like you just have a labeled data set and then you're going to take your favorite machine learning algorithm and apply it to that labeled data set. In active learning, collecting the data is part of the machine learning algorithm, and so that kind of gives you some more demanding system requirements. One of the ways that we've tried to allow researchers and practitioners to prototype active learning ideas is we built this open source software system that allows you to easily build up active learning systems. A lot of people have used it for many different applications. I'm just going to tell you about two of my favorite applications that I've been involved with where we've really seen active learning give helpful gains. One has been in active learning to optimize crowdsourcing in the New Yorker Caption Contest. And I'm not going to say much more about this, but if anybody wants to talk to me during the breaks or afterwards, I could tell you more about our collaboration with the New Yorker using active learning for crowdsourcing. And another one, this is a fun one that came out of one of my former students, Kevin Jamison's work. He decided he wanted to implement some active learning in the real world, so he built an app for the iPhone, which was a beer recommendation system. And basically, it actively learns a user's preferences for beers quickly. And again, the Next system and this app are both free. So if you're interested in checking them out, no charge. So I'm not trying to milk you for money or anything here. All right. So what I want to do with the rest of this first part is just kind of go into a little bit of some of the basic principles of active learning. Some of the theory, just touching on it at a kind of high level, and then Steve's going to dive more into kind of more complex ideas in more detail. So to begin with, one of the things or ways I like to think about active learning is by distinguishing between what I call what and where information. So in the case of just learning a density, what information would be something like, what is the conditional probability of y given x? So here I'm showing you, say, y is a label, x is a feature. That's the conditional probability function. A where question is, where is this conditional probability function greater than 0? So that would be basically telling us what's the decision set for label equal, say, +1 instead of -1. Okay? So what information, in this case, what is this function versus where does this function have a certain property? Another what and where example is just in straight up density estimation. We could say we want to estimate the density of our data, x, or we could ask where is that density greater than some value epsilon. That's something you might want to do if you were doing clustering. And then finally, we could think of a function estimation case, like we want to estimate or learn what is the conditional expectation of y given x. That's a what question. A where question would be where is the maximum of that function. So for what value of x do we have a maximal reward? And this is basically the bandit setting. So it would be a certain location. So the point of this slide is just to kind of impress upon you that one of the most effective places for active learning is situations where you want to learn about where information. You want to localize something, a decision boundary, a maximum of a function, the support of a function, something like that. So all of these kinds of problems, clustering, bandits, and just general classification and prediction, have active learning versions. We're going to be focusing mainly on classification, and especially on binary classification, just to keep all of the math and so forth clear and as simple as possible. But a lot of the principles and ideas we'll be talking about can generalize to many, many different situations. Okay, so here is kind of a meta algorithm, if you will, for active learning. And it basically works like this. Suppose we have a collection of models or hypotheses. I'll call that script H. So that's the set of all models we're considering. If you want to keep something in your mind, think of all possible linear classifiers in some feature space. And then we're going to basically iterate over a kind of loop in which at each step we're going to first sample a random sample from the data set, from the unlabeled data set. We're going to then label only those examples that distinguish models in our current hypothesis class or version space. And then we're going to reduce that hypothesis class or version space by removing all models that are inconsistent with the labels we've received. And then we'll repeat this process until we've sort of winnowed things down to a small pool of very good models, or maybe just a single model, and output that. So here's how it looks in a picture. It's sort of this loop. So we have a model space. That's why I was calling H. We look at that model space, the structure of it, the geometric structure, what have you. We use that structure to decide how to select examples for labeling. We ask our human expert to label those. We get those labeled data, and then we use those labeled examples to prune or narrow our search over this model space, basically effectively reducing it. And again, this reduction is because we're throwing out models that are inconsistent with the labels we've received. So let me give you like the very simplest example of this. This would be learning a one-dimensional classifier. So what I'm showing you here, these dots are supposed to denote unlabeled examples. And you could imagine that if we labeled all of them, we could learn a nice linear classifier. So this would be, for example, if your blood pressure is above a certain level, then you probably have heart disease, and the red would indicate that. So we can contrast passive learning and active learning very easily, and I'll show you these two. So passive learning would just be randomly selecting unlabeled examples for labeling. And active learning, in this case, could be implemented just as a binary search or bisection procedure, where we keep trying to sample between the two closest oppositely labeled points. And you can see after a few samples, the binary search, the active procedure, has really nailed down where that decision boundary is, but the passive one is sort of very, very loose. It hasn't really figured out where to put that decision boundary. And in fact, just a little back of the envelope math shows you that the error of the passive learning method goes down like 1 over n, where n is the number of samples you've collected, versus the active method, binary search, is going down like 2 to the minus n. So we get an exponential speed up in how quickly we can learn from a small set of labeled examples. So this is kind of the classical starting point for trying to understand why active learning could help, and that's binary search. So then you can say, well, that's great. I learned about binary search in my freshman computer science class. Is that all there is to it? Well, there's a lot more to it. We're going to tell you about that. But the starting point for just saying how would we generalize binary search to more complicated situations is VC theory. And so let me just give you a kind of little bit of an introduction to this, and then Steve's going to talk a lot more about the theory of active learning in the next couple of parts. So suppose we're giving a set of training data x, y, so those are our labeled examples, and we want to learn a function f to predict y from x. So we're going to consider a possibly infinite set of hypotheses. I'll call it script f. I guess I was calling this script h before, so my apologies for changing the notation a little bit. But basically I'm saying suppose we have a big pool of hypotheses or models and they have a finite VC dimension, d. And so if you aren't familiar with VC theory, just think about D as the dimension of your feature space. That's what it would be in the case of a linear classifier, for example. So we have with that, for every F, for every model in this class, we can talk about its error rate, and we'll call that the risk. And so that's just the probability that f of x is not equal to y for a new pair xy. So the first thing you can do is you could say for any f, I could look at how well does it do on the training data. So this r hat of f is simply counting up how many mistakes do I make on my training set and then normalizing by n to get an average. We call this the empirical risk. And what VC theory does for us is it allows us to bound uniformly over all the models in our class the deviation or difference between the true probability of error or true risk and the empirical risk of each and every classifier f. And so this bound is saying that the maximum absolute difference between r and r hat for any f is less than or equal to 6 times the square root of that VC dimension d, and then there's a log factor there, log n over delta, divided by n. N is your sample size here, and delta is your confidence level. So we think of delta as some small number like 0.01, like 1%. We want to have 99% confidence that this bound holds. So how do we use something like this? So this is empirical risk minimization. I'm sure many of you are familiar with it, but bear with me. I just kind of want to go through this, and then I'll talk about how we activize this type of procedure. So empirical risk minimization, the goal is to select a hypothesis whose true error rate is within epsilon of the best we could achieve from any element of this class script f. So I'm going to talk about 2 different classifiers. F star, which is the true risk minimizer. It's the F in our class that actually minimizes the true probability of error, sort of the test error, if you will. F hat is the model that minimizes the empirical risk. That's something we can actually compute by just looking at the training data. And so since F hat minimizes the empirical risk, we know that the empirical risk of F hat has to be less than or equal to the empirical risk of F star. Okay, so that's kind of the key insight. And what it allows us to do is make a picture like this. So what I'm showing you is the empirical risk of F hat and F star, those are the blue dots, and then those confidence intervals are the confidence intervals we get from the VC inequality I showed you on the previous slide. So basically what that's saying is that the true risk of F hat is somewhere within the red bars around the R hat of F hat blue dot, and similarly for F star. So what does that do for us? So now we can sort of say, well, what do we know? We know that the true probability of error, the true error rate of F hat, with high probability is going to be less than or equal to that upper bound there, which is R hat of F hat plus that term coming from the VC inequality. And we also know that with high probability, the true error rate of F star is, at best, this R hat of F star plus or minus that bound coming from the VC inequality. So we know what those upper and lower limits are, and with high probability, those are where those true risks or true probabilities of error sit. And so what we can do now is we can just look at the difference. Okay, so the difference between those two bounds is just 12 times the square root of d log n over delta divided by n, the sample size. And what that means then is we can immediately identify how many training samples, how many labeled examples do we need in order to find an epsilon good classifier, where we're going to need this difference to be less than or equal to epsilon. So that's where the 12 times the square root of that business less than or equal to epsilon. And then we just invert that to solve for what should n be. And we find that n should be something like d log 1 over epsilon, or d log 1 over delta divided by epsilon squared. So what is that telling us? It's saying that if you're in a higher dimensional feature space or a larger VC class, or higher VC dimension, you're going to need more training data. It also says that if you want to push epsilon down, if you want to get closer and closer to that true best classifier within that class, you're also going to have to pay a price in how many labeled examples you need. And Steve's going to be elaborating on all this as we go forward. So let me just show you how this might look in pictures then. So what I'm doing here is I'm showing you empirical risks of a bunch of different classifiers, say. Each blue dot is the empirical risk, and the red bars, again, are those confidence intervals coming from the VC inequality. So we could order them like this, from lowest empirical risk to highest empirical risk. And what happens as we collect more and more training data, we'll shrink these confidence intervals, because remember, those VC bounds are going down like 1 over the square root of n, or proportional to that. And we'll get to some point like this if we've got enough training data, and at that point we can clearly see that with high confidence, model 1 is better than all the other models. And that's the idea of empirical risk minimization. You could keep going until you get this epsilon good model, or you could keep going if you have a finite set of models until one's clearly better than all the others, like I'm showing here. So what's the issue? The issue is that empirical risk minimization may be wasting labeled examples. And why would that be? So let's kind of back up to where we started. Let's collect some more data, shrink those confidence intervals, and suppose we're at this stage right here. Now, what could I glean from this picture? Well, if I had this picture, I can see that at this point, we know that hypothesis 1, or model 1, has to be better, or at least with high probability, is better than model 3 and all the others beyond model 3, right? And so we could actually remove that from further consideration at this point, remove all the others. And we basically have boiled things down at this point to just a race between who's better, model 1 or 2, okay? So rather than continually asking for random examples at this point, we're going to kind of strategically select samples. We're going to only require labels for examples where hypotheses or models 1 and 2 label an example differently, where they disagree. And so this is the idea of disagreement-based learning. Steve is the world expert on this topic, and he's going to be talking a lot about it. But the idea is that now what the machine's going to do is it's going to say, okay, now I know. I just have to worry, is 1 or 2 better, model 1 or 2. I'm going to ask my human expert. I'm going to search through my data set of unlabeled examples, find examples where models 1 and 2 predict different output labels, and I'm going to ask the human expert to label those. Those are the ones that I'm confused about, me being the machine in this little story. So let me show you how that might look, and this is based on some of Nina's work, actually. How would you do this disagreement-based active learning in the case of a linear classifier? So what we're going to do here is consider points or unlabeled examples sprinkled uniformly on the unit ball in this picture, and we're going to focus on linear classifiers that pass through the origin or the center of this ball. So that's what one of the classifiers looks like. We don't know which one it is, so it could be in any orientation. So now what we're going to do, we're going to follow this empirical risk minimization idea. We're going to take a bunch of examples, draw them at random from our pool of unlabeled cases, ask our human expert to label them, and say we get these red and blue dots. So now what does that mean? It means that we know that the only linear classifiers that could be consistent with these labeled examples are the ones I've shown here. Okay? All the others we can rule out because they start to misclassify things. So what we're going to do then is we're going to focus now on this region where new examples might distinguish among those remaining hypotheses. This is the region of disagreement. We're going to now look at it. The machine will go and look at a large set of unlabeled examples remaining in that data set. But it's not going to label all of them. It's only going to label ones in the green region, in the disagreement region. So it's going to say, forget about all those, just label those two, and update your hypothesis. So we improve it a little bit. And to improve it, rather than having to label a bunch of examples, we focused our sampling and only labeled two here. And so that's the idea of disagreement-based learning. And basically, what you can say about that is kind of this sort of general type of result. And again, Steve's going to go into a lot more in a moment. But if we assume that our Bayes classifier, the optimal classifier for our problem, F star, is in this VC class with dimension D, and we have some nice distribution, for example, the label noise is bounded. I don't want to get too much into these details. We can talk about it later if you like, but we're going to assume those two nice things, and we're going to let epsilon denote the difference between the error rate of F hat and the error rate of the best Bayes classifier, F star. So if we were in this kind of situation and we use the normal passive learning machine pipeline, then our error after n samples would be roughly like d over n. The dimension of our problem, the VC dimension, or the dimension of the feature space, just in a simple linear classifier problem, and that's what we call the parametric rate, d over n. If we're active, though, the error goes down much faster. It goes down exponentially fast, just like it did in that binary search example. It goes down like e to the minus some constant c, n over d. And so we get this exponential speed up in how quickly we can learn a good classifier or good prediction rule in this case. Okay? So that's what I wanted to say in this first part.